In this video, we're going to introduce one of the most important functions that we're going to spend a lot of time thinking about in this chapter, and that is a function that's called enthalpy. So what is enthalpy? All right, mostly we've been talking about energy, and we often, we call that E, and we often think about, are we increasing, decreasing energy? Why are we introducing this new function? Well, enthalpy is related to energy. Enthalpy is given the symbol H. This is the symbol for enthalpy, and is defined as energy plus P times V, whereas energy, of course, is defined as Q plus W. Now, if you remember, W was equal to negative P delta V, and we can see there's a relationship here, right? The P and the pressure and the volume show up here as well. For our purposes, the most important thing, though, is that at constant pressure, which is going to be pretty much everything we consider in chemistry, a change in enthalpy for a system is equal to the heat. And we often write that with a little subscript P to indicate this constant pressure part. That's what this P is for. And so this means that enthalpy gives us a way to calculate or keep track of heat that's exchanged between a system and its surroundings. I mentioned that we often aren't going to worry about the work too much. And so there are cases where the work is not negligible, where we can't ignore it. And so enthalpy gives us a way to think about just the heat. Whereas if we think about not Gibbs energy, but just energy here, we're going to have this work that we have to worry about. Why is this useful? Well, we defined enthalpy, H, E plus PV. These are all state functions. Energy is a state function. The energy in a system, potential or kinetic, just depends on how fast things are moving and what are the potential energies, whether from positive and negative charges or from gravitation or things like that. And pressure and volume, it doesn't matter how a system gets to a certain pressure or a certain volume. Those are also state functions. So enthalpy is a state function, just like energy is. And this is going to end up being quite useful. We'll get to this later in the chapter, but it allows us to construct paths to get from point A to point B that maybe aren't very realistic, kind of like our example when we were thinking about state functions and we had our mountain, right? Thinking about a path where, say our goal is to get from point A down here to point B at the top of the mountain, to figure out what's the change in energy here, and for some reason we can't figure that out directly. Well, what we can do is, if we can figure out how much energy it takes to, say, get up into an airplane. Let me draw my airplane here. There we go. That's our bad airplane. And then, we go up to point C here, and then we take a parachute down or something. But we arrive at point B. It doesn't matter how we got there. If we can figure out A to C and then C back to B, if we can figure out this arrow and then this arrow, that allows us to find the overall change in energy. And in this case, also enthalpy, which tells us about the heat involved in a reaction. So enthalpy, as it's related to energy, also is in units of joules or joules per mole. If we're talking about enthalpy for a mole of something, either reacting. And there are a few different types of enthalpies that we'll think about in this class. So we'll have enthalpies related to chemical reactions. Let's just do a list of some of these enthalpies that we can think about. So we'll have delta H, and we'll often write an RXN, short for reaction. So so this will be heat involved in a chemical reaction. We'll also have enthalpies related to phase changes. So enthalpies of, for example, what we call vaporization or fusion. Vaporization being boiling, fusion being melting, or freezing. We can also think about condensation, right? So, but the heat involved with a phase change. And one additional type of heat exchange that we will think about and look at in the next video is enthalpy is involved with just heating or cooling something. So this one doesn't get a special subscript, but delta H involved with heating or cooling. Maybe we want to know how much energy does it take to warm up a pot of water, or how much energy does it take to cool down a can of soda. Right, so there are enthalpies associated with that. There's heat exchanged because there's a change in temperature. Right, and that's our definition of heat, is that it's energy exchanged because of a difference in temperature. So if we have something hot and something cold and we put them together, we want to figure out how much energy is exchanged. So these are types of enthalpies that we'll see. And you'll notice all of these enthalpies all have a delta symbol in front of them. It's kind of difficult and sort of arbitrary to talk about just H, like the enthalpy without a delta. It's kind of hard to calculate that because you sort of have to think about what's the energy in all the kinetic energy and thermal energy. But it's relatively easy to calculate a difference in enthalpy, a change in enthalpy. And one thing I just want to emphasize when we're thinking about deltas, so delta H, this would involve H final minus H initial. And anytime we see a delta, it's always delta whatever is going to be final minus initial. So what's the final state? And it's important to keep track of this because we will see enthalpies that are either positive or negative. We will see, just like we can have heats that are positive or negative, and keeping track of your signs is really important. And so always final minus initial, not initial minus final, because then you'll get the opposite sign. One last thing I just want to reiterate here. We talked about the idea of endothermic and exothermic processes in a previous video, but this applies to enthalpy just because enthalpy is equal to heat. So a delta H that is negative is what we call an exothermic process, and this means it's energy leaving the system. We define work the same way. If work is done by the system, if the energy leaves the system because the system is doing work, that's also negative. But we're mostly going to focus on this and the idea of heat. So energy leaving the system. Whereas delta H being positive is what we call endothermic. And that's energy coming into the system. Now, because that's happening with the system, exothermic processes will cause the temperature of the surroundings to increase, and endothermic process will cause the temperature of the surroundings to decrease, because the energy is coming out of the surroundings into the system that will cause the temperature to go down. So in the next video, we'll look at an example of how do we actually calculate enthalpies and introduce also the idea of heat capacity.